Okay, chemists, let's do some practice problems from NMR spectroscopy, combining things like molecular formulas and IR spectroscopy, and see if we can deduce some structures. Starting off with this one, we've got 10 carbons, 11 hydrogens, a bromine, and 2 oxygens. I like to label what the IR signals signify first. 3050 and 2950, those are CH bonds, respectively sp2 and sp3 CH bonds. 1740 is a carbon-oxygen double bond. Not sure what type of carbonyl just yet. That's right on the border between things like ketones and esters, but it's probably one of those. Let's look at the Proton Nmr, a pair of 2 hydrogen doublets. That's a para-disubstituted benzene ring. We've seen that multiple times. That means we have a benzene with 4 H's on it and 2 other things. I don't know what they are yet, but that would make sense. The next thing that stands out is this 3 hydrogen singlet. A singlet means no neighbors. The location of that singlet in the 3s suggests this is an O CH3 group. I don't know what else is attached to that, but that's there. And then the remaining 1 hydrogen signal and 3 hydrogen signal, look at the splitting pattern. This 3 hydrogen doublet means 3 hydrogens have 1 neighbor. This 1 hydrogen signal looks like a quartet. That means 1 hydrogen has 3 neighbors. So if 1 has 3 neighbors and 3 have 1 neighbor, they must be paired. They must see each other, which means they're connected to each other. So what would that look like? That would be a carbon with a CH3 group and then an H on it attached to 2 other things. That's everything in the Proton Nmr. Let's go back and take a look at the molecular formula. We're actually missing a couple of atoms. There's a bromine somewhere in the molecule. And remember, there's a carbonyl, as indicated by the IR spectrum. So we have a CO double bond somewhere in the middle. Now it's a matter of putting these pieces together and doing a little trial and error and seeing what order makes the most sense. I like to think about it in terms of which parts bookend the molecule. Where does this start and where does this end? Namely, the bromine and the methoxy would be the 2 ends of the molecule. And then somewhere in the middle are these 3 other pieces, the para-substituted benzene, the carbonyl, and this what's called methine. That means a carbon with 1 H on it. There's actually 6 different ways you could sort those combinations to give you 6 different constitutional isomers. And I'll show you one and explain why I think it's not the correct answer, and then we'll close with what the correct answer is. We could have the bromine connected to the methine, connected to that para-substituted benzene, connected to a carbonyl, connected to the methoxy. So this actually fits the integration and the splitting, and most of the signal location makes sense as well. The O-methyl, the para-substituted benzene, this methyl. The one thing that stands out that I think would be too tough for the purposes of what we're learning in this class would just be the location of that H. I think that H would be more electron poor than it currently is. I see this hydrogen, that's this one right here at around 3.6, 3.7. I suspect that this would probably be more electron poor, likely more electron poor, due to the fact that it's both benzylic and on a carbon attached to a benzene. That's probably well into the 4s, maybe even the 5s on the ppm scale of the x-axis. Again, I wouldn't expect us to actually know that. We don't have enough experience with this. So frankly, any of those 6 constitutional isomers, I'm not drawing them all, but any of the 6 constitutional isomers that you would get from putting these pieces together, I would consider correct. I'll show you what the correct answer actually is. It has a bromine directly attached to the benzene, followed by that methine, and lastly the carbonyl, making this an ester. That is actually the correct answer, and it's that location, the location of this hydrogen right here being benzylic and alpha to the ester. Those compounded facts make me feel like it's probably in the 3s. If it was just benzylic or just alpha to the carbonyl, it would probably be in the 2s. But because it's next to both of them and a slightly electron poor benzene ring, moreover, because of the bromine attached, it's probably close to 4. We'd have to actually have more information if we wanted to confirm that this was the structure. So I started off with a particularly challenging one on this problem set. This just highlights that sometimes, even with all of this spectral information, it's still a pretty divergent question, and we don't necessarily know exactly what the true structure is. We would have to do some reactions or get even more spectral information, things that we haven't learned yet, such as two-dimensional NMR, to figure out what the true structure is. The rest of these are much more convergent. You'll see that we'll get a pretty conclusive answer for each one. So with that, let's go to the next one. C5H9Br, let's start with the IR spectrum. IR shows CH bonds, respectively sp2 and sp3, right above and right below 3000. 1600s is a CC double bond character. That makes sense. The first thing I see in the NMR spectrum is a vinylic hydrogen. In the 5s, that's going to be a hydrogen on a carbon-carbon double bond, most likely. And then what else do I see? I see a 2-hydrogen doublet. That means there's 2 hydrogens which see one other. Oh, like that one right there. So maybe there's a CH2 directly attached to the alkene that I just drew. That would make sense. Lastly, we have 2 3-hydrogen singlets. So I have a CH3 and a different CH3 somewhere. What else is in this molecule? Look at the molecular formula. We have a bromine somewhere. So those are my pieces of the puzzle. I gotta put them together in some sequence that makes sense. Just confirm that we've got all the atoms taken account for. There should be 5 carbons, 1, 2, 3, 4, 5. Should be 9 hydrogens, 6 plus 3 more make 9, and our bromine. Yep. How do I put these together? Well, there's 3 spots on this largest fragment off to the left and 3 remaining pieces. Now, think about the splitting to help you figure out where each of them must exist. I can't put a methyl on this end right there, because if I did, I would get a 3-hydrogen signal that would be split into a triplet, and that's not true. I see only singlets. So those methyls must be off of the alkene. They mean I have no neighboring hydrogens. They would be split into nothing. They'd be singlets, which must mean that the bromine is out there. There's the molecule. Let's draw it off to the right as a line structure, and we can confirm everything that we see. We have a 3-hydrogen singlet, another 3-hydrogen singlet, there they are. We have a 1-hydrogen triplet, there it is, and we have a 2-hydrogen doublet paired right next to it, there it is. Makes sense that it's pretty de-shielded, pretty electron poor. Those 2 hydrogens are both allylic and next to a bromine, so the location also makes sense. The carbon NMR matches as well. All 1, 2, 3, 4, 5 of those carbons are in a unique environment. So I spy 1, 2, 3, 4, 5 separate signals, and each one is accounting for 1 carbon alone. Even those 2 methyls are not identical to each other. They're in slightly different environments. That methyl is cis to the H on the alkene. That methyl is trans to the H on the alkene. So they show up as slightly different alkene carbons off to the left. Sorry, those are the alkene carbons off to the left. Those 2 allylic methyls are elsewhere. One of those 3 over there, 2 of those 3 over there. Okay, so those are the first 2. Let's flip to the back. There's 4 more. I'd like you to hit pause and see how many of them you can come up with, and then come back and check. I'll go over them. Okay, let's take a look. Big molecule to start with, C10H14O. What does the IR tell us? We have sp2 CH bonds a little above 3000, sp3 CH bonds a little below 3000, 1600 carbon-carbon double bond character. No carbonyl, no alcohol. We would see that in the IR spectrum. Remember, the absence of signals is just as informative as the presence of signals in all of this spectral information. First thing I notice in the Proton Nmr is this pair of doublets. That's another para disubstituted benzene ring with 4 H's arranged symmetrically, opposite 2 other groups. The next thing I notice is a 3-hydrogen singlet in the 4s. That's probably an O CH3. That would explain why it has no neighbors. It's attached to an oxygen. And the location being between 3.5 and 4, that's probably hydrogens on a carbon attached to an oxygen. Lastly, I have a 6-hydrogen doublet and a 1-hydrogen multiplet paired with each other. That's an isopropyl group. That's a C with 2 methyls and a single hydrogen. So those 6 see 1 neighbor, and that 1 sees 6 neighbors. I suspect that means this is, even though it says multiplet, it's probably a septet. It's just hard to resolve, so they wrote multiplet on this. And that's everything. That's all the atoms that are present in the molecular formula. We've got 10 carbons. That's all 14 hydrogens and the 1 oxygen. There's only one way those pieces can get put together. We've got a methoxy, a benzene, and an isopropyl. And that's our molecule. You could just ask yourself one challenge question like, how do I know that that's where the oxygen is? Couldn't I get a constitutional isomer that puts the oxygen in between these two carbons? Yeah, but then I think that would reverse the location of this singlet and this septet. They would be swapped in terms of where they occur. And that exists, that molecule exists, but it's not this arrangement. So you can kind of confirm everything at the end and look at the signal location to really conclude that you have the right structure. Not even looking at the carbon NMR, but I'll close with it. I spy 1, 2, 3, 4, 5, 6, 7 signals, but there's 10 carbons. Yep, by symmetry, we have some similar carbon atoms. Those two are in the exact same environment for the isopropyl group. That must be that signal over there. And then 2 of these benzene carbons are going to be identical, and 2 others of these are going to be identical. Those must be those 2 signals accounting for 4 carbons right there. So these 2 signals are actually 4 carbons. You can tell because the signal's height is double the other signal height. If everything was the same height, each signal is probably just 1 carbon, but once you see a signal that's double the height, it's probably worth multiple carbons. In fact, it's usually quantitative. Double height, double the number of carbons. Okay, moving on. Next one, C8H14O. IR shows sp2CH and sp3CH bonds. 1710, that's a carbonyl, probably a ketone or an aldehyde, a little low on the 1700s. If it was in the upper 1700s, it might be like an ester or an acid chloride or something. 1600 carbon-carbon double bond character, and that's the first thing I'm going to make sense of in the Proton Nmr. I spy a vinylic hydrogen, similar to what we saw on the front. So we have an H directly on an alkene. What else do I have in the Proton Nmr? I spy two hydrogen signals. One of them looks to be a triplet. The one right next to it looks like it's a quartet. They're not labeled, but you can zoom in and look at those and see the splitting pattern. And that tells me how many neighbors that they have. The rest of these are 3 hydrogen signals. Those must be methyls. They're too low, too far to the right to be O-methyl groups. Plus, we've already accounted for the 1 oxygen. It's the carbonyl. So we have a carbonyl somewhere in this molecule. We have 3 methyls, and then we have 2 CH2 groups. Let's talk about those 2 CH2 groups. I haven't drawn them yet. One of them, the triplet, has 2 neighbors. Oh, so it could be next to the other one. The other one is worth 2 hydrogens, and it apparently has 3 neighbors. It's a quartet. So it's either next to one of these methyls, or it's next to this one and those 2. Now, a quartet implies it has 3 neighbors, but if those 3 neighbors are on one single carbon, in other words, if this signal is next to one of the methyls, then the methyl would see that and be split as well. And I don't see that. I don't see a triplet for any of these methyls. So I don't think this 2 hydrogen signal is next to a methyl. I think it's next to 2 other carbon groups where you have a total of 3 hydrogens between those 2 different neighboring groups. Let me say that again. If this quartet was due to the fact that it was next to one of the methyls, then one of the methyls would be split by these 2, and they're not. All 3 of them are singlets. So that's all I know. I know that these 2 hydrogens are not next to one of the methyl groups. But there are 3 other hydrogens that could account for this quartet, and I could put this quartet in between those 2. So I think we have a CH2 and then another CH2 connected to this alkene. So all 3 of those signals correspond to this really big piece in the middle here. That takes care of all the hydrogens. I think it even takes care of all the carbons. It should be 8, 4, 5, 6, 7, 8. That's everything. I have to figure out how to put them together. This is a lot of pieces, but 3 of them are the same. Just 3 methyls, and all in similar environments. Looks like they're next to doubly bonded carbons, 2 much more similar to the 3rd one. So where are they? Well, I can tell you where one of these methyls is not. There is not a methyl on this end, because as we said a moment ago, if it was there, it'd be split by those 2 into a triplet, and I don't see that. So the methyls must be off of the alkene, and then the carbonyl. That's the only thing that would cause them to be singlets, because there's no neighboring hydrogens on those doubly bonded carbons. That must mean that I just stitch these two things together, and that's our molecule. Let's draw it. So we have a methyl and another methyl, both attached to the same alkene carbon, a CH2, and then a methyl ketone on the end. That's our molecule. And if I look at the carbon NMR right underneath that drawing, every single carbon is in a unique environment, so I see a total of 1, 2, 3, 4, 5, 6, 7, 8 different signals. 8 signals. 8 carbon signals, because all of those carbons are in a different chemical environment. Even the two methyls that are off of the carbon-carbon double bond are slightly different. One being cis to the H, the other being trans to the H. They're somewhere in the sp3 carbon range off to the right. You could make sense of some of the others. There's the carbonyl off to the left. There's the alkene carbons right in the middle in the 130s or so. Okay, 2 more to go. The next one, C5H11BRO, very boring IR spectrum. All I see are CH bonds. That's sp3 CH bonds, isn't it? Because it's a little below 3000 to the right. The molecular formula, before I forget, has a bromine in it somewhere. And then what else do I have? Well, I have a big 6 hydrogen doublet and a 1 hydrogen multiplet. That's an isopropyl group. We saw that earlier. Because 6 hydrogens have 1 neighbor and 1 hydrogen have many neighbors. They wrote multiplet, but it looks to be like a septet. If you zoom in and count, I think you'll find that that's what you have. What's left? Two hydrogen triplets. So 2 hydrogens see 2 others, and 2 others see 2 hydrogens. So they must be right next to each other, a CH2 and then another CH2. And what else do I have? Wait, the molecular formula has an oxygen in it somewhere. In fact, I know exactly where it goes, because remember that isopropyl group we just pointed out? Look at the location of that methine hydrogen. That H is pretty far to the left, up in the 3s. That means that H, which is this one, is attached to a carbon, which is further attached to a pretty electronegative atom, like an oxygen. So I think this isn't an isopropyl, this is an O isopropyl group. And now that's every part of the molecular formula. We have to put them together. There's only one way to do it. It's this CH2CH2, which is surrounded by a bromine on one side and an O isopropyl on the other. So bromine, CH2, CH2, and then O isopropyl. Check. Everything in the NMR matches, even the carbon NMR. We have some symmetry. Those 2 carbons are in the same environment, so they would show up as 1 signal in the carbon NMR. So I would count this as 1, 2, 3, 4 signals, but that one off to the way, all the way to the right counts as 2 carbons, and that's how you still get 5 carbons for your molecular formula. Last one, C8H7N. What does the IR show us? We have sp2 CH bonds above 3000, sp3 CH bonds below 2200. We haven't seen that in a while. That's a triple bond. That's either CC triple or CN triple, and then 1600 looks like carbon-carbon double bond character. I don't have an alkene. Look at the proton NMR. I have a benzene ring. In the 7s, that's a benzene ring, plus there's 5 hydrogens. This is not a paradise substituted benzene. This has 5 hydrogens, so this is a phenyl. We have, and they're all kind of in similar environments. Not exactly the same, that's why it's not a singlet, but 5 of them. In an ideal world, I would resolve 1 signal for that hydrogen, 1 more for those 2, and 1 more for those 2, but they're all buried right on top of each other, so it's just 5 hydrogens adding up together. What else do I have? I have a 2 hydrogen singlet. I can tell this is a singlet, so there's a CH2 group with no neighbors. That takes care of 6 plus 1, that's 7 of the carbons. We have 1 more carbon. Aha, yes, there's a triply bonded carbon somewhere. So we have a triply bonded carbon. It's not a carbon-carbon triple bond because we've run out of carbons, and check the molecular formula, you need a nitrogen. So this is actually a nitrile. We have a CN triple bond. and that caps off the other end of the molecule. So we have a phenyl on one side, a nitrile on the other, and they're flanking a CH2. Let's draw it and confirm. Benzene, CH2, C-triple-N, that should be the structure. Very simple NMR spectrum. 5 hydrogens in the aromatic range, 2 hydrogens singlet. Yep, no neighbors. Those 2 hydrogens don't split each other, and they're not split by anything on adjacent carbons because there's no hydrogens on the adjacent carbons. Check the carbon NMR by symmetry. You should see a signal for the nitrile carbon, another signal for the methylene, another one for that carbon attached to the cyanomethyl, one more for those 2 carbons, one more for those 2 carbons, and then one last one for that. So I think I should see 1, 2, 3, 4, 5, 6 signals in this carbon NMR. 1, 2, 3, 4, 5. Looks like there's another one buried in there. Yep, there are 6, but a total of 8 carbons. Again, because of symmetry, some of the carbons show up as the same signal, buried on top of each other. That's something we're very used to in proton NMR. We don't see it as much in carbon NMR because most of the times the carbon atoms are in slightly unique environments that they show up resolved. But with symmetry, you can have them show up in the same spot. Okay, so that's hopefully helpful. A lot of practice questions to deduce structures from spectroscopy. Thanks for watching.